This topic, which is related to agri-environmental policy, concerns the issue about how do you contract for an environmental public good with private landowner owners. The framework that we use is the principal agent model, and we're going to look in detail at this relatively simple model here, which is where a farmer has a profit function which relates to the provision of labour or effort into providing a conservation area of 1 hectare, and there's a regulator, the government, who have to pay the farmer for this effort, and then we work through this in various different steps. So first of all, we just assume that the regulator and the farmer know everything. So the regulator sees what the farmer's costs are, and then if that's the case, then they can offer the farmer a contract, and then the question is, well, how much effort do they want from the farmer? And it turns out that that's fairly straightforward. And then the next step is that we look at the issue of moral hazard, where the regulator can't observe directly how much labour the farmer puts into providing the conservation area. So there's a danger that the farmer will be offered a contract but will actually cheat on that contract. So that's the moral hazard, or the hidden action problem, and we show how you can solve that. And then the next problem is the problem of adverse selection, which is where you have two farmers, a high cost type and a low cost type, but you don't actually observe their types. So if a regulator is trying to offer each farmer the best contract for their cost type, then it ends up that the low cost farmer will choose the contract for the high cost farmer, and there'll be a loss of efficiency. So that's called adverse selection. So this is a very important problem in relation to providing conservation from private land, and it's been widely explored in the US, Europe and Australia. Okay, so let's start off by having a look at the basic problem. So this is the Mathematica code, and this table here defines the profit function and the regulator's objective function, and then it just defines various parameters. The cost of monitoring, it mentions that a fine might apply if there's non-compliance, and it also defines the effort, which is effort in days per year. So this is a relatively simple problem. Okay, so here we define the profit function, and I'll just explore this in a different pane where I can actually draw the farm's profit depends upon their type. So in this case, this is the well, let's say this is the profit for type 1, and it's equal to B0 minus B1 and then E squared, where E is the effort into conservation. Now we can distinguish between the two farm types in a variety of different ways, but if we look back up here, then specific cases of the two farms or the two farm types are that we this parameter B01 and B11 specifies one farmer, and there's another one B02 and B12 specifies the other farmer. Now you'll notice that if E is equal to 0, then it's really straightforward, because profit is just equal to B01, and B01 is the profit from farming with no conservation. So that's quite important, because it defines how well the farmer can do without that contract. And if the contract that's offered is not better in total than the profit from farming, then the farmer won't accept it. Okay, so that's defining the profit function. Then we define these parameters here. So A is the value to the regulator of the conservation effort. SPPF is the shadow price of public funds, so that indicates the cost of raising taxes. CM equals 10 is the monitoring cost, and fine is equal to 10 is just an initial value for the fine for non-compliance, but we'll come on to that. So this graph shows the profit, and it shows that as the effort increases, then the size of the transfer that's needed to compensate farmers for engaging in conservation increases. And this can be represented by what's called the individual rationality constraint, which is where the profit with conservation effort plus the compensation paid by the government must be greater than just farming without conservation. And you'll notice that this simplifies down to say that the transfer cost must be greater than or equal to B1T ET squared. That is, it must cover the opportunity cost of this effort. Okay, so that's the basic model with from the farmer's side. Now, if we just go to the regulator, then the regulator's objective function includes AE, which is the benefit from the conservation effort, so in terms of additional biodiversity, less the transfer cost minus the shadow price for public funds, so this penalty on using taxpayers' money, plus the profit that goes to the farmers. So the regulator cares about three things. So it cares about biodiversity and has a value for that, A. The regulator doesn't like paying out taxpayer money, so that's this shadow price for public funds times the transfer payment, C. But it does care about farmers, so there's farmers' profit in that objective function. Okay, so now we can, and you might sort of anticipate this from elsewhere in ENVT4402. Now we can put this into a mathematical programming problem. So we got the regulator's objective function, we've got the profit function, we've got the same for the other producer, and then we can just use that to determine an optimal solution. So I just need to make sure that that this objective function is evaluated, and then we can evaluate this block of code here, and all that's happening there is basically the individual rationality constraint is going in as a constraint, and it's different for both producers. And then we can have a look at the results. And so we can have a look at EOPT1. So I just need to make sure that that is style code. So if we evaluate that, that's equal to 4.5439. If we evaluate EOPT1, then that's also equal to that. So we define all these terms here, so that we've got the optimal effort for farmer type 1, the optimal effort for farmer type 2, and we can have a look at those. So farmer type 1 has got an effort of 4.54 days. Farmer type 2 is an effort of 2.2 days. The transfer to farmer 1 is 20, the transfer to farmer 2 is 10. All right, so what the regulator wants to do between the low cost and the high cost farmer, so farmer 1 is the low cost and farmer 2 is the high cost, is it wants to offer separate contracts so that farmer 1 puts in more effort in return for a larger transfer, and farmer 2 puts in less effort in return for a smaller transfer. In terms of these optimal policies, then we can evaluate them in terms of symbolic solutions, and it's always useful to do this because it can be quite revealing. So what we've done here is we've taken the partial derivatives. We've got the Lagrange multiplier, which introduces a constraint on the individual rationality, and the symbolic solution with these particular functions is that the marginal cost for society contracting with these farmers for more effort is just equal to the benefit. And the slightly strange form of this function here is just adjusting for the shadow price of taxpayers' funds. So actually, let's just take this a bit further. So so what we're doing here is we're taking the partial derivative of the effectively we're taking the partial derivative of the profit with respect to the effort. We're adjusting it for the fact that shadow price of public funds. we're adjusting it for that, and then we're equating it with the value. So this is one of these things in economics which is called a marginal condition, and it determines the optimal contract. But the thing about it is that it depends upon the regulator being able to observe the farmer's costs of effort. So that's this parameter here, B1. Okay, so that ends part 1 of these recorded lectures for topic 4.